Hi everyone. Today I will speak about voice biometry, what are the current research approaches, and what are the technology that is used in production nowadays. What is the voice biometry for? This technology can be used in many applications. Quite wide use is search in audio archives. Basically, if you need to find a speaker and find some recordings, it's one of the modality you can use. It is used in caller authentication in contact centers to make the authentication more personal or more convenient. Nowadays, there are voice assistants, basically smart speakers or voice bots, and you would like to get personalized answer. So the voice biometry is used there too. Application is fraud detection, because there are situations for small loans over internet or internet or over a phone, and there are organized groups that tries to basically get the money instead of you. So voice biometry is one of the tools that can be used to fight these frauds. And of course, it is used in criminology, where, for example, you have some calls, there is a bomb somewhere and so on, and you need to basically get the knowledge if it was this person or other person. In case of voice biometry, what we are doing, basically, we are trying to build the model of human from inside. The air is going through the vocal tract, and it's modulated, and through this modulation we are producing sounds. And the goal of voice biometry is to such model just from observation of the acoustic pressure, some vibration of air. So usually we start with some recording. So we have a mic and record waveform. What are the next steps? The waveform is usually chunked to small parts, 20 or 30 milliseconds long, and then we do some parametrization. We calculate spectra, so many of you knows. So we have wave chunk. We calculate the similarity with different harmonics and get some vector, and this vector is called spectra, and we can put this spectra each next to each other, and we spectrogram. So we have we converted the waveform to image. Of course, the human ear doesn't have the same resolution on each frequency. So what we are doing, we say that the lower frequencies are more important than the higher, and we use triangular filters. So the image transformed, and the higher frequencies are less important. Then we need a model, but to build a good model, we need a lot of data. So what data do we need, and how it is collected? We would like to have technology that can be used all around the planet. So we need data from many nationalities all around the world, and we need several recordings with the ID. So it is quite interesting. The technology is already more accurate than humans. So we need to verify the speaker using other metadata than just speech. So either using ID or other possibilities to use image. Basically, it is possible from voice only. So in our case, we train on more than 12,000 speakers, and the data are collected by us, but we license the data from LDC. That there are free databases. So basically we use everything, but still it's not enough. We would like to model different variation of the speech. So we do so-called data augmentation. So we add real additive noise, music, people speaking on background, reverberation, basically reflection of the audio from walls. We change the speaking speed and so on, and create even more data that is used for training. Then what is the neural network architecture that we use? Before there was architectures that were very successful and were using Gaussian mixture models, and one of them was called iVectors. But in these days, neural networks wins. So current state-of-the-art architecture is basically a neural network architecture, and we start with the spectrogram. After that, the audio is processed in some smaller chunks, let's say frames. So we use neural network on frames. Here it's named ResNet 34. After that, but we need to work with variable length recordings. So we do some collection of statistics. Here it is called mean and variance pooling over time. And after that, we add a few more layers of neural network here. This already classify fixed length vector to speakers. So our training data is chunked to 4-second audio, and we try to collect or to classify this to a close set of speaker. It's large set, but it's finite. The pipeline is implemented in PyTorch, and it takes about 1 week to train it on 6 NVIDIA cards. But if we want to work with the system, we don't want to just to classify from a closed set of speakers. So what we do, we basically use something that is called bottleneck features or embeddings. We cut off few final layers of the architecture of the neural network, and we use the internal representation as our speaker model. It's basically floating point vector with 256 values. Now, why ResNet? Maybe actually it's a very known architecture from image processing. So it was found that this architecture works well on speaker identification too. It is using convolutional layers and there are skip connections basically that address vanishing gradient problem. In this ResNet 44, there are 44 layers. So we were using other architectures, more layers. So one of them was with 128 layers. It gives better accuracy, but also higher complexity and system footprint. What is the criteria function or the error function? One possibility is cross entropy, but in our case, we are adding also additive angular margin criteria function. This basically improves the quality of the speaker embedding, that then you can use more simple tools for comparison of these speaker models. So it is also possible to use cosine distance just between two speaker models, and it works very well. So it can be used for clustering and similar tasks. Another approach is probabilistic linear discriminant analysis that can be used for comparison that is already trained model. I will speak about it in a while. So what is the user view on voice biometry? Basically, we have two modules. One is speaker model extractor or voice print extractor that takes input audio and produce speaker model. It can be done in real time. You don't need recordings. It can work with live audio and so on. The second model is comparison. So you have two speaker models. You have comparator, and you will get some similarity. I called it here raw score. The comparator can be cosine distance. It can be the probabilistic linear discriminant analysis. What is PLDA about? It came from face verification, and the basic idea was that the face can be composed from several components as basically linear combination. So we have mean face, and then you have some bases that reflects the between individual variability, basically how the faces or people differs from each other, and then there is a component that adds the individual variability, how the phases can change because of different light, view angle, and so on. How is this model used for speaker comparison? We basically take two hypotheses. One is if the two speaker models came from the same speaker, and the other hypothesis if two speaker models came from different speaker, and we can evaluate the probability of this hypothesis and calculate likelihood ratio. So our score is likelihood ratio. Here I have a map. How is it done? So basically, the speaker model or speaker embedding is a linear combination of speaker variability and channel variability, and each can be modeled by Gaussian distribution. And we have mean and two covariance matrices, and one is for within class or individual, and the other is for across class variability. And then we can evaluate the likelihood ratio. Other module that is in the system is calibration. Either we start with the raw score, for example, cosine distance, or for example, we would like to apply the system on some data that are farther from our training set. So in this case, we need that brings the score to better probabilistic interpretation. And in this case, we can use, for example, logistic regression to make the score better calibrated. For logistic regression, we need training set where we have pairs of speaker models, and the answer, if it is matched speaker or if there are different speakers. And if we have such set, we can train such a transform, and we can get well-calibrated score. So now how to basically how to evaluate that the system works well, and or how to measure the performance of such system. So usually we have a data set again with pairs of speaker models and information if it is matched or if there are different speakers. So it's called target trails or non-target trails. And we pass this through the model, through the system, and get the score. And after that, we can compare the score with a threshold, and then the decision if that it's either matched or if it's rejected, it's the same speaker or different speaker. So after that, we can basically evaluate basically have threshold, and we can evaluate errors. So the errors are that we either the system set it's not a speaker, but it is the same speaker, this is miss, or the system said it is the same system, but it is the same speaker, but it was not, so it's false alarm. I can demonstrate it if the score is above the threshold, and it should be the same speaker. It's here correct. It's a green dot. If it shouldn't be the same speaker and it's below the threshold, it's a red dot, but we can get errors that is falsely accepted or falsely rejected or missed. So we can have the probability distribution of these two cases, and we can draw the probability of false alarm and probability of misses to one graph. So the graph is called detection error trade-off. It's something like row curves, but with different scale on axis, and you can see that if we change the threshold, we are getting a curve. If the curve is closer to the origin, then we are getting better system. So you can see that there are different operation points, and you can prefer to set differently based on the use of the system. So for example, if we need high security, for example, for bank transfer, we will set it to small false alarm rate. If we are searching for information and we want to be sure we are not missing any information, we will set it to low miss probability. And the point in the middle is equal error rate, where both errors are the same, and it is used for a system evaluation very often. So there are international evaluations, and you can see the results from them, like evaluation by National Institute of Standards and Technology in USA. There is a VoxLab challenge on YouTube videos, and there is also short duration speaker verification that evaluates both text-dependent and text-independent systems, and with the goal of some authentication. What is important, people often ask what is the system error, but it's good to know that the error depends on the amount of speech, amount of evidence that you provide to the system. So the longer recordings you have, the higher or the lower error rate you will get. And the system performance is decreasing year by the system error is decreasing year by year. So here we did a long-term evaluation of our systems. So here you can see that the error rate is decreasing basically exponentially. In 2000, there was GMM systems, GMM with universal background model. In 2006, people start to explicitly model channel variability. In 2008, there was two components, channel and speaker variability model in some subspace. After that, there was simplification in I-vectors. There was one vector modeling the recording variability, and the system was very successful before the new network-based systems came. In 2017, the system, basically the new network-based system, as I presented here, came, and these are the winning system now. So in the later years, there was more tuning using higher spectra, higher sampling frequency, more data, and so on. I'm getting a question: what is the error rate of such system? If it is good enough or not? So I like this image. Basically, the MIT guys trained speaker ID system to get speaker model, but then they use neural network to transform the speaker model to face model and to use their system to reconstruct the faces. And you can see that in the first column, there is the original picture, then there is a reconstruction from and then from speaker model. And you can see that the speaker model contains quite a lot of information. So you can see that you can clearly recognize it if it is male or girl, what is the age, and so on. Now I would like to tell you a little bit more about artificial or fake voices, because it's a related problem, and people ask usually what are the trends here. So I will speak about network-based synthesis, voice modification, in synthesis, real-time voice modification, and a little bit about detection of fake voices. So current speech synthesis are also based on neural network. There are several neural networks. For example, one is used to transform text to some character embedding and to transform character embedding to spectrogram or Mel spectrogram. And then there is other neural network, often called vocoder, that takes this Mel spectrogram and transform it to speech. And with such system, you already are not able to recognize if it is pronounced by human or by synthesis. Of course, it depends how well the network are trained, but we are about the situation where the person is not able to tell, especially the person doesn't care and it's not listening carefully. So this is a detailed architecture of such system, basically that could run from Google. It's encoder-decoder architecture with attention. So you can see blue, the encoder part, then there is attention decoder part, and the final part is the neural network that transforms Mel spectrogram to waveform. So, and what if you want to change the voice? Usually it's not difficult. You can take speaker model that was extracted exactly in the same way as for voice biometry. And you can concatenate this model with the input to one of the neural network and train the system. And after that, you can change the voice of the synthesis. Again, here is the detail architecture. So before the attention layers, you are concatenating the content embeddings with speaker embedding and send to father. Okay, this was how to synthesize audio with different voices. If you don't need or don't want to enter text, it is also possible to enter audio. Basically, you will replace the first neural network with either recognizer or basically some encoder, and get the internal representation that can be phonemes, characters, and so on. And if you train these systems together, you can get a system that will basically change the voice in real time, that you can speak in your voice and get the voice of, for example, famous actor. And how is this complementary to voice biometry? So what we can see that the error rate of voice biometry decreases rapidly. So we are able to detect some speakers well, or we are able to search for some content better. But the voice biometry does not care about if it is real or artificial voice. So this is okay for application like voice search or personalization, where it is not important. It is bad or harder for caller authentication because we need to do anything else or something more with it. So the common approach is that we train one more new network to recognize if it is real or synthesized speech. So we need training data for it. Actually, but what is the difficulty here? We are also transferring our telecommunication networks, and here we are using compression, we are using some codecs, and in this codecs there is also analysis and synthesis. So then we are distinguishing whether it is good or bad speech synthesis. So this is widespread codec CELP that is in most of the devices today. So here to distinguish whether is there this synthesis, it's quite easy because you have a fixed code book and you have some model parameters or filter parameters, and it's easy to detect it. But there are also new codecs like Google IRA that is starting to use artificial intelligence too. So we have also WaveNet in the decoding part, and it starts to be more and more difficult to distinguish if it is WaveNet for speech synthesis or if it is WaveNet for audio transfer. Okay, so what are the current challenges in speaker recognition? The systems work well with close talk mics, but with far field speaker verification, it's more difficult because there is more audio distortion, and this segment needs more research. Also, the diarization or basically segmentation of audio to speakers in time. We have less training data for our models, and the systems are not there, but it's harder to use them commercially. Of course, we would like to be also able to do some source separation if we have audio and for example, music and speech. We would like to separate these two. There is we are getting the speaker models, but also we would like to know how good are the speaker models. So it's other research direction. There is always research in the new network architectures. We have a good architecture, but be better. And in these days, there is a lot in pre-training of the neural network on more data, basically with unsupervised training and so on. So other information, basically, what else can be in audio? So we were speaking about speaker identity, but there are more like gender, age, language, alcohol consumption. You can recognize disasters, recognize COVID, emotional state, or even person height, and so on. So the voice biometry and the information that is in voice is quite wide. So to conclude my talk, I would say that voice biometry is machine learning task where machines overperform humans significantly. You can recognize a human by machine well, but human has difficulty. we are able to build quite accurate models of human being just from acoustic observation, from something that you don't need to touch the person. And a lot of information is still hidden in the human voice, and it awaits for researchers to explore this information and to use it for some human benefit. So thank you for your attention, and I am waiting for your questions.
So I would like to thank Petr for a very nice presentation. I'm stopping the recording.